Before there was light, there was darkness. Not the kind you find by closing your eyes, nor the familiar shadows cast by the moon. This was a profound, absolute void, a universe that had yet to learn how to shine. The story of our cosmos usually starts with a bang, the Big Bang, a term that brings to mind a fiery, brilliant explosion of creation. But the truth is, for hundreds of millions of years after that initial moment, there was no light at all. No stars, no galaxies, nothing to see. Imagine a vast, invisible ocean of hydrogen and helium gas, stretching endlessly in every direction, cooling and expanding in the silence. Astronomers call this mysterious period the cosmic dark ages. It's the time after the initial blaze of the Big Bang faded away, but before the very first stars flickered into existence. It was an era without light, without complex structures, and without any witnesses to its silent grandeur. But this darkness wasn't empty. It was patient. Within that primordial soup, the invisible force of gravity was already hard at work, tirelessly pulling matter together. Tiny, almost imperceptible fluctuations in the density of the gas began to grow. Over millions of years, these slightly denser regions acted like cosmic seeds, attracting more and more hydrogen. Think of it like subtle currents in a still ocean, slowly gathering stray particles into unseen clumps. These weren't yet stars, but they were the cradles where stars would be born. The universe was like a sculptor, quietly and methodically shaping its first masterpieces in complete darkness. The silence of this era was deceptive. It was a period of immense preparation, setting the stage for the most spectacular light show in history. Then, after what felt like an eternity, something incredible happened. Inside the most massive of these collapsing gas clouds, the pressure and temperature reached a critical point. A point so extreme that hydrogen atoms were forced to fuse together, unleashing a tremendous burst of energy and light. The first star was born, and then another and another. These were not like our sun. They were giants, hundreds of times more massive, burning incredibly hot and intensely blue. They lived fast and died young, exploding in spectacular supernova that forged heavier elements like carbon, oxygen, and iron for the very first time. These explosions sent shockwaves through the surrounding gas, triggering the formation of new stars and eventually entire galaxies. The cosmic dark ages were over. The universe had switched on the lights. This transition from darkness to light wasn't just a beautiful event. It was the most important transformation in cosmic history. The light from these first stars traveled across the universe, rayonizing the neutral hydrogen gas and making the cosmos transparent just as we see it today. The heavy elements scattered by their explosive deaths became the building blocks for everything that followed. They were the raw materials for new generations of stars, for planets, and billions of years later, for life itself. Every atom of carbon in your body, the oxygen you breathe, the iron in your blood was all forged in the heart of these first stellar giants. We are, in the most literal sense, made of stardust. Our story didn't begin on Earth. It began in the dark, with those first pioneering stars that ended the cosmic night. Today, astronomers use incredible tools like the James Webb Space Telescope to peer back in time, searching for the faint, ancient light from these first galaxies. It's like being a cosmic archaeologist, digging through 13 billion years of history to find the first glimmers of dawn. By studying this era, we're not just learning about the distant past, we're uncovering our own origin story. We're understanding how a dark, simple universe evolved into the rich, complex, and light-filled cosmos we inhabit. From a silent, dark void to a universe teeming with billions of galaxies, it's a journey of unimaginable scale. And it all started with that quiet, patient darkness, waiting for the first star to set it ablaze. Have you ever wondered what the universe looked like right after the Big Bang? Was it a brilliant explosion of light? Well, the truth is a bit more complicated, and for a very long time, the cosmos was plunged into an era of profound darkness. To understand why, we have to travel back to the very beginning, to the end of the universe's first light. Around 380,000 years after the Big Bang, the universe underwent a monumental change called recombination. Before this, the cosmos was an incredibly hot, dense soup of subatomic particles. Free-floating electrons and protons were everywhere. and they acted like a thick fog, constantly scattering photons, particles of light. Light couldn't travel more than a few inches before being bounced off in a random direction. The entire universe was opaque, trapped in a blinding, chaotic haze. But as the universe expanded, it cooled. When the temperature dropped to about 3,000 Kelvin, something amazing happened. The protons and electrons finally had a chance to connect, forming the first neutral atoms of hydrogen and helium. Suddenly, with no more free electrons to get in their way, the photons were set free. They streamed across the cosmos, finally able to travel unimpeded. That ancient light is still with us today. It's been stretched and cooled by billions of years of cosmic expansion, and we now detect it as the cosmic microwave background, or CMB. It's the oldest light in existence, a faint echo of creation. For the first time, the universe became transparent. But this wasn't the start of a bright, starlit cosmos. The light from recombination wasn't from stars or galaxies. It was the fading ember of the Big Bang itself. Over eons, it has dimmed into microwaves, completely invisible to our eyes. And so, after this brief moment of transparency, the universe entered a long, quiet, and dark chapter. Cosmologists call this period the cosmic dark ages. The universe was filled with a thin, uniform gas of neutral hydrogen. But there were no stars to shine, no galaxies to illuminate the void. Imagine being there. The sky would be utterly, completely black. Now you might think this darkness was perfectly uniform, but it wasn't. There were tiny, almost imperceptible ripples in the density of the gas, left over from quantum fluctuations at the dawn of time. These fluctuations were minuscule, like a difference of 1 part in 100,000, but they were the seeds of everything to come. Regions that were just slightly denser than average began to exert a tiny bit more gravitational pull. Over immense timescales, they started to attract more hydrogen and helium gas, slowly but surely. However, this process was in a constant battle with the expansion of the universe itself, which was trying to pull everything apart. For hundreds of millions of years, gravity fought a slow, patient war. These subtle density ripples slowly grew into vast, invisible halos of matter, the future cradles of galaxies. During this era, the universe was dominated by that neutral hydrogen gas. Hydrogen atoms, in their ground state, don't emit or absorb visible light. They are, for all intents and purposes, invisible. The only radiation zipping through space was the CMB, which had already redshifted far beyond the visible spectrum. The universe was filled with a cosmic fog, but not like any fog on Earth. It was incredibly thin, less dense than the best vacuum we can create in a lab, but it stretched across billions of light years, absorbing any stray high-energy radiation and ensuring the darkness remained absolute. For stars to form, this gas needed to do more than just gather. It had to cool down and collapse under its own gravity, becoming dense enough to ignite nuclear fusion. As the universe expanded, it naturally cooled, but there was a problem. Hydrogen atoms are actually very bad at radiating away heat. Without heavier elements like carbon or oxygen, which act as efficient coolants, the cooling process was incredibly slow. This is why the Dark Ages lasted for so long, for hundreds of millions of years. The universe was patiently waiting for enough gas to collect in the right places, within gravitational wells created by mysterious dark matter, and for that gas to cool sufficiently. This long silence wasn't a pause, it was a preparation. The cosmos was setting the stage for its next great act. Every star, every galaxy, every planet, and even life itself traces its origin back to this dark, quiet beginning. Without the cooling and settling of that neutral hydrogen, the magnificent structures we see in the cosmos today could never have formed. The Dark Ages were the silent, essential groundwork for everything. Within that cold, dark expanse, the blueprints for the first stars were being drawn. And then, after hundreds of millions of years of darkness, somewhere in the vast, empty void, a cloud of gas finally reached the tipping point. It collapsed, compressed, and grew hotter and hotter until, in a brilliant flash, nuclear fusion ignited. Star was born. And with that single point of light, the universe began to wake up. The cosmic Dark Ages were over, and the dawn of the first stars had finally arrived, ready to illuminate and transform the cosmos forever. From the cold, silent darkness of the early universe, the very first light emerged. This wasn't the flash of galaxies or vast clusters, but tiny glimmers of ignition deep inside, collapsing pockets of hydrogen. These were the first stars, cosmic pioneers that would end the darkness and begin an era of illumination we call the cosmic dawn. They are known as population 3 stars, and though none have ever been seen directly, their fingerprints are written all across the universe. Roughly 100 to 200 million years after the Big Bang, gravity began to win its ancient struggle. Within the densest knots of hydrogen, gas clouds collapsed inward, heating up as they fell. The process was fierce. As matter compressed, temperatures in the core skyrocketed to tens of millions of degrees. Finally, atomic fusion ignited, the same process that powers our sun, but on a scale almost beyond imagination. The first stars were born, but these were not ordinary stars, or monsters. Population 3 stars were likely hundreds of times more massive than our sun. See? The early universe had no heavier elements, what astronomers call metals. It was almost entirely hydrogen and helium. Modern stars use metals like carbon and oxygen to cool down and fragment during their formation, allowing many smaller stars to be born. Without these elements, it was much harder for primordial gas clouds to fragment. So instead of forming clusters of smaller stars, they often produced just a few colossal ones. The result? Stars with masses ranging from 30 to maybe over 300 times that of our sun. They burned ferociously hot and blue, with surface temperatures exceeding 100,000 Kelvin far, hotter than any star we see today. They lived fast and died young. These titans of a pristine universe lived for only a few million years, mere blink in cosmic time. Their immense size meant they burned through their hydrogen fuel at an astonishing rate. But in those few million years, they completely transformed their surroundings. They unleashed torrents of ultraviolet radiation, powerful enough to tear electrons away from neutral hydrogen atoms, a process called reionization. Slowly, massive bubbles of ionized gas expanded around each new star, carving glowing pockets into the dark, foggy hydrogen of space. This marked the beginning of the epoch of reionization, a gradual, universe-wide transformation where light once again conquered darkness. As more and more stars formed, these ionized bubbles grew and started to merge. The universe was changing from opaque to transparent, not through cooling this time, but through sheer, overwhelming illumination. These early stars also kickstarted another critical process, chemical evolution. When they died, they didn't just fade away. Many ended their lives in hypernovae explosions far more energetic than the typical supernova we see today. Some may have even collapsed directly into black holes, planting the seeds for the supermassive giants that now sit at the heart of nearly every galaxy. Their spectacular deaths forged the very first heavy elements: carbon, oxygen, iron, the raw materials that would one day form planets and life itself. Before the first stars, the universe was simple, containing only hydrogen, helium, and a tiny trace of lithium. After them, it had the ingredients for complexity. Think about this. Every atom in your body, heavier than helium, the carbon in your DNA. The iron in your blood, the calcium in your bones was forged in the heart of a star like one of these. The first stars may be long gone, but they seeded the entire cosmos with possibility. As the first generation of stars came and went, they left behind enriched gas, now containing those crucial metals that made cooling and star formation much easier. This allowed the second generation of stars to be born smaller, longer-lived, and capable of forming in much greater numbers. Clusters of these new stars began to gather together within massive halos of dark matter, creating the first protogalaxies, small irregular gatherings of light. Each protogalaxy might have contained only a few million stars, a tiny fraction of the mass of our Milky Way. Yet these early systems were the first organized structures in the universe, the direct ancestors of all galaxies to come. Through billions of years, they merged again and again, drawn together by gravity into ever larger systems. Over time, this cosmic assembly line built the vast, beautiful galaxies we see today. In that sense, our own Milky Way wasn't born all at once. It's the product of countless ancient collisions. A grand descendant of those first tiny sparks that lit up the cosmic night. But the universe wasn't just forming stars and galaxies. It was developing structure on the grandest scale. Simulations and observations have revealed that dark matter shaped the large-scale pattern of the cosmos, forming vast filaments of invisible mass that connect nodes of galaxy formation. These filaments created the cosmic web and immense network, spanning the entire observable universe. With galaxies clustering along its threads and vast, empty voids in between. The cosmic web is the very architecture of the universe, the skeleton upon which all the luminous matter we see is arranged. And it all began in this early epoch, when gravity and light began their eternal dance. As the first stars and galaxies multiplied, their combined radiation finally finished reionizing all the gas between them. By about 1 billion years after the Big Bang, the universe was once again filled with light. The primordial hydrogen fog had been completely torn apart by radiation, allowing ultraviolet light to travel freely across the vastness of space. In their place stood a young, luminous cosmos galaxies, forming, merging, evolving in a beautiful ballet of gravity and light. This was the dawn of the visible universe, the beginning of the cosmic story we can still piece together today with our most powerful telescopes. But many mysteries remain. What exactly were those first stars like? How massive were they? How many of them were there? And when did that very first light truly appear? These are questions that no human eye has yet answered directly. But our incredible instruments are getting closer every day. The first stars no longer exist, but their light echoes through time. Their radiation sculpted the universe, their explosive deaths enriched it, their descendants became everything we know and see today. Every star that shines in our night sky carries a trace of their ancient legacy. From darkness, they created light. From simplicity, they created complexity. From chaos, they created the cosmos. But the universe has not given up all its secrets. Even now, astronomers across the globe are searching for the first faint flickers of that ancient dawn, hoping to one day witness the moment the universe lit up for the very first time. We call it the first light, the moment the universe broke its long darkness. But when exactly did that light appear? It seems like a simple question, yet it cuts to the deepest mysteries in cosmology. For the universe, light is not just illumination, it is history. Every photon tells a story of what existed, how far it's traveled, and what it encountered along the way. And when we search for the first light, we are really searching for the moment creation became visible. If you ask, when did the first light appear? Science doesn't offer a single date. There was no cosmic switch flipped one day to end the Dark Ages. Instead, the dawn came slowly and evenly, locally and chaotically. It began with the first stars, scattered across a vast, dark universe. Each star illuminated only a small bubble of space around it. When a few such bubbles grew and overlapped, the first regions of the universe became transparent to ultraviolet light again. But elsewhere, darkness remained. This patchwork transition, bright islands in a sea of darkness, lasted for hundreds of millions of years. It's what cosmologists call the epoch of reionization. In some regions, stars formed early, perhaps just 100 million years after the Big Bang. In others, conditions weren't right until hundreds of millions of years later. So, when did first light truly appear? The honest answer is, gradually, between 100 million and 1 billion years after the Big Bang. The universe transformed from a foggy darkness to a transparent, glowing cosmos. But the details who lit the first candle, when and how remain hidden in that distant past. Astronomers debate which objects produced the earliest light. Were they the massive population 3 stars, living fast and dying in powerful explosions? Or did early black holes, the remnants of those very stars, accrete gas and shine as brilliant quasars, outshining entire galaxies? The truth might involve both. In one view, the first stars, enormous, short-lived, and fierce, were the primary engines of reionization. Their ultraviolet light ionized hydrogen, creating growing spheres of transparency. This theory fits with what we know about the intense radiation such stars would produce. But there's a problem. These stars died quickly. To maintain the process of reionization, new generations had to form continuously, meaning early galaxies must have been surprisingly efficient at birthing stars. The second theory argues that the earliest black holes, formed when the first massive stars collapsed, powered the dawn through their accretion disks. As gas spiraled inward, it heated to millions of degrees and emitted X-rays, capable of ionizing hydrogen over much larger distances. If true, the first light of the cosmos may not have been starlight at all, but the glow of matter falling into black holes. It's likely both processes worked together. Starlight may have ignited the first sparks while black holes amplified them, slowly transforming the universe into a luminous web. To truly solve this mystery, astronomers look not for visible light but for radio shadows. Neutral hydrogen, the element that dominated the Dark Ages, absorbs and emits radio waves at a specific wavelength, 21 centimeters. This is the key to unlocking the cosmic dawn. As the first light appeared, hydrogen gas began to absorb or emit this 21 centimeter signal in distinctive ways, depending on how it was heated, ionized, and illuminated. By mapping this signal across the sky, scientists hope to watch the Dark Ages end to see the universe's light switch flicker on in real time. But there's a challenge. These signals are faint, incredibly faint. Earth's radio noise, satellites, and even our FM stations easily overwhelm them. Detecting the 21 centimeter signature from billions of years ago requires extraordinary sensitivity and often complete isolation from human-made interference. Projects like EDGS, LAFER, and the Square Kilometer Array are attempting this feat, aiming to capture a faint dip in radio frequencies that could correspond to the moment the first stars turned on. In 2018, the EDGES experiment claimed to detect such a signal, a mysterious, unusually strong absorption feature that might correspond to the birth of the first light around 180 million years after the Big Bang. If that signal is real, it would mean the first stars formed even earlier than we thought. But the result remains controversial, awaiting confirmation from independent observatories. Even with our most powerful telescopes, the earliest epoch remains beyond direct view. The universe's expansion has stretched the light from those first stars to infrared, wavelengths invisible to human eyes and detectable only by the most sensitive instruments. Until recently, the farthest galaxy known dated to about 400 million years after the Big Bang. But the James Webb Space Telescope has pushed that frontier closer to the beginning, spotting galaxies that may have existed only 250 to 300 million years after the Big Bang. Still, these are not the very first. Somewhere before them lies an uncharted period of twilight between darkness and dawn that no telescope has yet seen. These hidden epochs are like lost chapters in a book we can almost read. We know what came before, the Dark Ages. We know what came after, the luminous, structured universe of galaxies. But the middle, the instant when the lights first came on, remains one of the greatest frontiers in science. Here lies the cosmic paradox. First light of the universe. The most important turning point in cosmic history is the hardest to see. It's not because it wasn't bright. Its early stars and black holes were blindingly luminous. It's because time and expansion have stretched and dimmed their light beyond easy reach. Imagine watching a bonfire from across a vast ocean. By the time its light reaches you, it's only a whisper of faint warmth, buried beneath waves of noise. That is how we see the early universe today. We may never directly witness the first star ignite, but through the glow of ancient galaxies, the whispers of 21 centimeter radiation, and the deep infrared gaze of telescopes, we are learning to reconstruct that lost dawn. Even as our technology advances, profound mysteries remain. When exactly did the first star ignite? Current estimates suggest around 180 to 250 million years after the Big Bang, but no direct confirmation exists. How massive were the first stars? Were they hundreds of times larger than the Sun, or smaller, clustered together in primitive swarms? How quickly did galaxies assemble? Did they form gradually or explosively in a short, bright burst? What role did dark matter play, and what became of the first black holes? Some may have merged, forming the seeds of the supermassive black holes at the centers of modern galaxies, including our own Milky Way. Each question pulls us deeper into the same central mystery: how the universe's first light shaped everything that followed. There's something poetic in this pursuit. We beings made of stardust are trying to see the moment stars first appeared. Our curiosity is a form of cosmic recursion matter that became conscious, looking back at its own origin. The universe hid its first dawn behind unimaginable distances in time, yet we build machines and theories to pierce the veil. We search for the first light not only to understand the cosmos, but to understand ourselves. Because that first light, however, faint is where every atom that makes us began its journey. We do not yet know precisely when the universe first lit up, but we do know the light never truly went away. It expanded, it stretched, it cooled, and after 13.8 billion years, it still reaches us, crossing the void, whispering of beginnings. When we look at the stars, we often imagine beginnings, the birth of planets, the spark of life, the origins of everything we are. But our story doesn't start with our sun. It begins long before, in the profound darkness that followed the Big Bang. These cosmic dark ages weren't just an empty pause in history. They were the foundation upon which every habitable world would one day be built. To understand how Earth came to exist and why the universe can support life at all, we have to go back to that cold, silent era when the elements of possibility were first being assembled. Life as we know it requires three essential things: the right elements, the right conditions, and the right timing. During the Dark Ages, none of these existed yet. There were no carbon atoms to build molecules, no oxygen to form water, and no silicon to make rocky worlds. The universe was made of almost nothing but hydrogen and helium, the simplest elements you can imagine, yet this simplicity was necessary. It allowed gravity to work its magic on vast scales, unimpeded by the complexity of heavier elements. It allowed matter to gather cleanly into the first stars, whose fiery hearts would forge the very ingredients life would one day need. The Dark Ages were a kind of cosmic incubation, the universe cooling, organizing, and setting the initial conditions for everything that was to come. Had the universe been even slightly different if it had expanded too quickly, or if its initial density fluctuations were smaller, the first stars might never have formed. Too fast, and matter would have thinned out before gravity could clump it together to smooth, and there would have been no seeds for galaxies to grow from. But the cosmos balanced itself with extraordinary precision. Tiny irregularities, just one part in 100,000, became the foundation of all cosmic architecture. From those almost imperceptible ripples, galaxies and stars emerged, and with them, the conditions for life. When the first stars finally ignited, they began the process that would eventually make Earth possible. Inside their cores, nuclear fusion transformed hydrogen into helium. And in their final violent deaths, they created the first heavy elements: carbon, nitrogen, oxygen, iron. Each, these essential building blocks, was born in the heart of a dying star. As these first stars exploded, they seeded their surroundings with the ashes of creation. New generations of stars then formed from this enriched material, more stable and capable of forming planetary systems. By around 1 billion years after the Big Bang, the universe had already begun recycling its own matter, transforming the raw simplicity of hydrogen and helium into the complex chemistry of worlds. The Dark Ages, therefore, were not a void. They were the womb of stellar evolution. Without that long period of cooling and collapse, the universe could never have produced the massive stars that birthed the elements of life. From that first generation onward, the universe entered a self-sustaining cycle. Gravity pulls gas into stars. Stars forge new elements. Supernova disperse those elements. And then new stars and planets form from that enriched gas. This cycle repeated countless times over billions of years. Each iteration increased the abundance of heavy elements, what astronomers call metals. By the time our sun formed, 9 billion years after the Big Bang, the universe was finally rich enough in these elements to build rocky planets, oceans, and biochemistry. It took the entire cosmic history before us all the forgotten stars, all the dust and debris of ancient galaxies, to make just one world capable of sustaining life. But elemental abundance is only half the story. The Dark Ages also determined the very structure of the universe, how matter was distributed, how galaxies would form, and how stable environments like our Milky Way could arise. If early gravitational clustering had been stronger, galaxies might have formed too quickly, becoming dense. Violent systems where stars constantly collided and supernova sterilized any emerging planets. If it had been weaker, stars might have remained isolated, never clustering into galaxies, leaving the cosmos sparse and dark. Our universe struck a delicate middle ground. There was enough structure to form galaxies and stars, but enough expansion to give them room to evolve peacefully. That perfect balance, set during the Dark Ages, would ultimately determine whether stable planetary systems and life could ever emerge. Another hidden gift of the Dark Ages was time. For nearly 500 million years, the universe did almost nothing visible. But in that stillness, hydrogen cooled, and the invisible halos of dark matter grew deeper. This delay gave the universe stability. When stars finally did form, they did so in environments that could sustain long-term evolution. Without that period of rest, early star formation might have been too chaotic, with stars forming and dying too quickly for complex structures to follow. It's a reminder that even on a cosmic scale, creation often requires patience. The universe waited in silence, so that when light finally appeared, it could last. Over billions of years, those ancient chemical seeds found new homes. They condensed into dust, then into planets, and eventually into molecules capable of self-replication. Every breath you take, every drop of water, every cell in your body carries atoms that were once forged in the first stars. The carbon in your DNA might have come from a massive supernova 13 billion years ago. The iron in your blood may have originated in one of the earliest galaxies. And the hydrogen, the most abundant atom in your body, is primordial. It has existed since the universe's first moments. When you trace life back far enough, it leads not to Earth, but to the Dark Ages themselves. To the time before light, when the cosmos was still deciding what it would become. Even the timing of the Dark Ages helped life exist. If the first stars had formed much earlier, the young universe might have reionized too quickly, stripping hydrogen gas from galaxies before they could form planets, effectively sterilizing the cosmos. If they had formed much later, the universe might have expanded too far, diluting matter so much that star formation became inefficient. Instead, the first light appeared at just the right time, when the balance between expansion and gravity allowed stars to form, burn, and enrich the universe. We often call Earth's orbit the Goldilocks zone, not too hot, not too cold. But in truth, the entire universe passed through its own Goldilocks moment, and the Dark Ages were the threshold. Billions of years later, intelligent life on a small blue planet would begin to look back, piecing together this cosmic origin story. Our telescopes, our physics, our chemistry, our attempts to understand why the universe allowed itself to become habitable. When we study the Dark Ages, we are studying the conditions of our own existence. Why stars exist, why elements exist, why there can be air, oceans, and thought. Every habitable world, every sunrise, every spark of life is an echo of that first dawn. The Dark Ages were not just a shadow to be escaped. They were the blueprint, the structure of galaxies, the elements of life, the very rhythms of time itself. All of them trace back to that silent era when the universe cooled and began to organize. Our planet, our sun, our very ability to ask where we came from, were all consequences of decisions made by physics nearly 14 billion years ago. And so, in studying that darkness, we are not looking into emptiness. We are looking into the origin of light, matter, and meaning. In the beginning, the universe was dark, and in that darkness, it prepared for life. For most of human history, the night sky seemed eternal, its stars fixed and unchanging. But we now know there was a time before stars, before galaxies, before light itself. So, the greatest challenge for modern cosmology became this: to see the unseeable, to find evidence of an age when the entire universe was completely dark. But how do you detect light that doesn't exist? How do you study an era that left almost no photons behind? This is where the story of human ingenuity begins, the story of how we learn to listen rather than to look. The cosmic dark ages aren't something we can photograph. Visible light, the kind our eyes and telescopes detect, simply wasn't around back then. So scientists turned to radio astronomy. It's a branch of physics that doesn't look for light but for signals, faint, stretched radio waves emitted by hydrogen, the simplest and most abundant element in the cosmos. Every atom of hydrogen can emit or absorb radiation at a very specific wavelength, 21 centimeters. This signal, once short and sharp, has been stretched by cosmic expansion over 13 billion years. Today, it appears not as 21 centimeters, but as radio waves meters long. Detecting this ancient hydrogen signal is like trying to hear a whisper in a roaring stadium. Earth itself, with all our cell towers, satellites, and radio noise, drowns out this faint cosmic echo. But astronomers persist. They build incredible instruments. not to see the dawn of the cosmos, but to hear it. One of the first big efforts came from arrays like LOFER in the Netherlands and Paper in South Africa. These telescopes spread hundreds of small antennas across vast landscapes, each one listening to a narrow band of radio frequencies. Their mission was to detect the global signal of the universe. This first light, that moment when hydrogen gas began to interact with radiation from the very first stars. Then, in 2018, a small, relatively simple experiment made global headlines. The EDGES project, short for the Experiment to Detect the Global Epoch of Reionization Signature, reported something extraordinary. They had detected a dip, a sudden absorption feature, at a frequency corresponding to a time roughly 180 million years after the Big Bang. If correct, this meant EDGES had captured the first evidence of starlight interacting with primordial hydrogen, the cosmic dawn. But there was a catch. The signal was twice as deep as anyone expected. This suggested that either something was cooling hydrogen far more efficiently than known physics allowed, or that something mysterious, perhaps even dark matter, was influencing the process. It was a moment of both triumph and caution. The scientific community erupted into debate. Was the signal real, or just instrumental interference? Others started refining new models to explain the strange, strong dip in the data. Regardless of the controversy, the message was clear for the first time. Humanity had brushed against the silence of the Dark Ages. The difficulty of this work can't be overstated. The cosmic 21-centimeter signal is roughly 100,000 times weaker than the radio noise from our own galaxy. Separating it from the foreground hiss of the Milky Way is a task of almost unimaginable precision. To do this, astronomers are building experiments in some of the quietest places on Earth. We're talking about the deserts of Western Australia, home to the Murchison Wide-Field Array, and the Karoo region of South Africa, where the Meerkat Array listens to deep space. And soon, in both places together, will rise the Square Kilometre Array, or SKA. This will be the most sensitive radio telescope ever constructed. When completed, the SKA will consist of hundreds of thousands of antennas, spread across entire continents, all operating as one colossal ear pressed to the very edge of the observable universe. It won't just detect the first stars. It aims to map the structure of hydrogen itself as it changed through time, tracing how light gradually broke through the darkness, pixel by pixel across cosmic history. While radio telescopes listen, other instruments are trying to see. The James Webb Space Telescope, launched in 2021, has already peered further back in time than any telescope before it. Its infrared sensors are designed specifically to detect the faint, redshifted light from galaxies that formed in the universe's first few 100 million years, and it has already delivered surprises. Within its first months, JWST found galaxies that appeared too bright, too massive, and too evolved for their place in cosmic time, some forming just 300 million years after the Big Bang. These discoveries hint that the cosmic dawn may have ignited faster and more vigorously than our models predicted. In other words, the Dark Ages may not have lasted as long as we once thought. Every new dataset challenges our theories, forcing physicists to revisit the very foundations of cosmic evolution. How fast could the first stars form? Were they truly massive and short-lived, as we believe? Or did smaller, fainter galaxies contribute more light than expected? For every answer JWST provides, it raises three new questions. So, across deserts and mountaintops, under quiet skies and through deep space, the hunt continues. We are listening for whispers older than galaxies, for the faint hum of neutral hydrogen, for the fingerprints of the universe's first dawn. And every signal, every pixel of distant starlight, carries a story, not just of matter and energy, but of our own relentless curiosity. In seeking to understand the cosmic Dark Ages, humanity is, in a sense, searching for its own origin story. Not the birth of life or civilization, but the birth of light itself. Because to understand the universe before the first stars is to understand everything that came after. The atoms that make up our world, our oceans, our bones, our breath, were once part of that same primordial hydrogen fog. We aren't separate from the Dark Ages. We are their descendants. The universe's Dark Ages ended long ago. But for us, the observers born billions of years later, the struggle to illuminate that era has only just begun. We stand on the edge of discovery, between the known and the unknown, armed with instruments capable of probing the universe's earliest, faintest light. The question is no longer asterisk if asterisk we can see the cosmic dawn. It's how clearly we can understand it, and what it will tell us about our place in the cosmos. The James Webb Space Telescope was just the beginning. With its giant 6.5-meter mirror and infrared vision, JWST has already rewritten our timeline of cosmic history. But its discoveries have also raised profound new questions. If galaxies appeared earlier and more mature than expected, then the first stars must have ignited even sooner. That means somewhere hidden deeper in the redshift lies a chapter of the universe's history we've not yet seen. A time when gravity had just begun to gather gas into the first shining clusters, the first true beacons in the cosmic dark. To find them, astronomers are preparing a new generation of eyes and ears, instruments that will work together across all wavelengths, from radio to infrared to X-ray, to build a complete, multidimensional portrait of the cosmic dawn. The next frontier is breathtaking. The Square Kilometre Array, or SKA, now under construction in Australia and South Africa, will be the largest radio telescope ever built. Its goal is to map the famous 21-centimeter hydrogen signal across the entire sky. This will trace how the universe evolved from a fog of neutral gas into a luminous, structured cosmos. The SKA won't just detect the dawn, it will map it in 3 dimensions. By capturing billions of tiny frequency shifts, it will reconstruct the slow, uneven emergence of the first stars and galaxies, showing how reionization, the return of light, spread like ripples across the early universe. Working alongside it, NASA's upcoming Nancy Grace Roman Space Telescope will provide a wide-field infrared survey. It will complement JWST's deep, narrow gaze with a panoramic view of early galaxy formation. Together, they'll create a mosaic of the universe's infancy, from individual stars to vast cosmic webs. And even beyond these projects, like LOVOR and HABOX, massive future space observatories still on the drawing board aim to go further. To capture direct light from the first galaxies, and perhaps even to study the conditions that made life possible on worlds that followed. We are, in every sense, approaching the true horizon of cosmic history. To understand why this search matters, we have to remember what first light really means. It's not just about seeing further into space. It's about reaching backward in time, to the very moment when the universe became knowable. Before the first stars, the cosmos was silent. There were no elements heavier than hydrogen and helium, no light to reveal structure. But when the first stars ignited, they changed everything. They forged the first heavy elements: carbon, oxygen, nitrogen, iron, the chemical seeds of planets and life. Their ultraviolet light ionized the fog of hydrogen, making the universe transparent once more. And when they died, they enriched the cosmos with the materials from which future stars, solar systems, and eventually living worlds would form. To find the moment of first light is to find the origin of the chemical universe, the moment physics became chemistry, and chemistry became destiny. Even now, the light from that first generation of stars is still traveling toward us. Each photon, stretched thin across time, carries a memory of the universe's awakening. The universe is not static, it is a record, written in radiation and structure. And we, its observers, are reading that record line by line. Our radio telescopes decode the faint hiss of ancient hydrogen. Our infrared observatories detect the glow of the first galaxies. Our particle detectors study neutrinos that escaped when the cosmos was still opaque. Every method, every instrument, is another way for the universe to look back at itself through us, because that's what this search truly is. A mirror turned outward. Why We're studying the beginning of structure, of order, of possibility. We're studying the cosmic prelude to ourselves. What we might discover in the next few decades? Whoa. And just refine what we already know, could overturn it entirely. If JWST and SKA reveal that stars formed even earlier than expected, we may need to revisit our theories of dark matter, gravity, and cosmic evolution. Perhaps dark matter didn't just guide structure formation. Maybe it cooled hydrogen, accelerated its collapse, or interacted in ways we've never observed. Alternatively, if early galaxies appear surprisingly mature, it could suggest that the laws governing cosmic evolution are more efficient than we thought, that the universe was somehow predisposed to form complexity quickly. Each scenario challenges a core assumption about how cosmic order emerges from chaos, and somewhere in that complexity, hidden between physics and time, lies the question that keeps cosmologists awake at night. Did the universe always intend to produce light? Or was it an accident, a fragile, temporary escape from eternal darkness? In a very real sense, our telescopes are time machines. Not because they move us through time, but because they let us witness time itself. Each observation is a reunion across billions of years of conversation between what was and what is. And yet the deeper we look into the universe's past, the more we recognize something profound. We are not just observers of cosmic history, we are its continuation. The same hydrogen atoms that filled the dark ages later formed our sun. The same nuclear processes that lit the first stars still burn in our own. And the light that once ended the cosmic darkness is now reflected in every spark of human curiosity and every lens we build, every question we dare to ask. The universe's dark ages lasted for hundreds of millions of years. But in that immense silence, the blueprint for everything that followed was written. The first atoms gathered. Gravity sculpted their destiny. When light finally broke through, it began a chain of cause and consequence that led eventually to life, to thought, to the act of wonder itself. We now know that the darkness of the early universe wasn't an absence. It was potential. The silence before the first note, the pause before the first sunrise. And when that first light appeared, it did not merely brighten the cosmos. It made it visible. It made it possible. Somewhere out there, light from the very first stars is still on its waist, still crossing the void, still whispering the story of how everything began. And we, creatures born of that light, are waiting to receive it. To hear the echoes of creation, to see the universe as it once was, and to remember that even the brightest dawn begins in darkness. Thank you so much for joining us on this journey to the beginning of time. If you're as fascinated by these cosmic questions as we are, don't forget to like, subscribe, and hit that notification bell so you don't miss our next exploration into the great unknown. We'll see you in the next video.